Thank you. I'm Brendan Mulcahy. I'm a research engineer. I'm the lead of the Learning Agents team at Epic Games, and let's learn about learning agents. So here's what we're going to talk about today. We're going to talk about why. Why did we make learning agents? Why should you care about it? How? How does it work? And what? What did we do in Fortnite using learning agents in our research project? So if you're here at the AI Games Conference, I can guess there's one thing that's true for all of us, and that's we love video games. We love playing games, we love making games, we love everything about games, right? Well, maybe not everything, because if we're here, maybe we should make AI better. I play a lot of strategic games, and I'm always disappointed when the AI has to cheat in order to be intelligent. It's a common trick that the AI gets extra gold, extra ammo, maybe even extra sensory perception. Making intelligent AI is hard, and it's totally understandable that we need to lean on these things to make it challenging. But can we do better? Can we solve this problem? And I think the answer is yes, but not with classic AI alone. We need more power. We need machine learning. And in particular, we don't need LLMs. We need reinforcement learning and imitation learning. So you probably forgot what this is because of all the LLM craze. But really briefly, reinforcement learning is inspired by psychology and operant conditioning. It's basically training a pet with treats. So we have an agent in our game, maybe it's a bot or an NPC, and we want to achieve some sort of behavior with it. So we're going to wire up the observations of our game world, wire it up to the actions, and then we're going to give it rewards whenever it does an action that matches the behavior we're trying to get. So that's going to be some sort of a function that we defined. And the agent's initially going to be taking a bunch of random actions, and as it gets those positive rewards, it's going to be reinforced. Those actions are going to become more likely, and over time, its behavior is going to become what our goal was. With imitation learning, it's a similar setup, but instead of using rewards, we have some other player or AI system that we're going to use as a source of data. So we're going to, let's say we have a player playing Fortnite, we're going to drop them in, have some code to grab the observations of what's going on around them in the game world, and then what actions are they taking, and we're going to use that data set to train our agent. So that's imitation and reinforcement learning in a nutshell. If you want to learn more about this, you're going to have to check it out online, because we don't have time. Let's go. So why use RL and IL? Well, there's many reasons why you might want to use it. These are three things that I care a lot about. How do we get agents to have human-like behavior in games? Well, I think imitation learning seems like an obvious way. We have humans play our games. We gather data about how they play. We train a model on their data, and that model will look a lot more human-like. We get the ability to customize bot intelligence. If we can collect data across a wide range of skill groups, we can use that as a parameter into our model. And then we can have our agents play like human-like in a very intelligent way. We can have them play human-like in a less intelligent way. And that's going to be a lot easier to get actually good behavior that is bad, as opposed to like fake bad behavior. And then maybe one other benefit is that using machine learning, this gives us the ability to retrain instead of having to always reprogram. So if you're creating, for example, a game as a service, and new content's coming, new levels, new whatever, your AI agents need to be able to play as part of that new content. And having programmer time is very valuable. Having them have to reprogram the agents to always keep up with the content is hard. So maybe if we put in the time and investment to set up a training system, we can trade off programmer time for computation time. And that could be a good trade for your company. So machine learning is extremely hyped up. And I'm a skeptical person, as I'm sure a lot of you are. And I want to try to, what's the word? I want to try to make you feel okay about machine learning, because I just want to say it's just one more tool in your toolbox. Everything you already know about AI is still valid. We're not throwing that all out and trying to say that machine learning is some magical tool that's going to solve all your problems. So here's an example in Fortnite. We might have these wolves programmed with classical AI. They have simple behavior. They're just going to be these non-playable characters. We're never going to have players play as them. We're not trying to make them human-like. However, we might have bots that are actually going to replace players in our lobby, and we want those to play in a human-like way. So maybe we should use machine learning for that. So again, use the right tool for the job. So here's some use cases. as I just mentioned with like Battle Royale, for example, you might want to have AI opponents to play against. That makes sense. You might want to have AI teammates, maybe solve toxicity by just not having humans on your team. Once we have agents that can play games, we can use them to do QA. QA your game in a realistic way, gather performance data, et cetera. And then one thing that I really like, and the reason I even got into this, was this idea of being able to do training and teaching games. So maybe you could make a game experience where you're the coach of a basketball team, and you have high school players who you're training them to actually get better at playing, and then you have your team face off against another team, or maybe battle bots or something like that, right? So I think those are really cool opportunities once machine learning becomes a lot more accessible. So let's talk about learning agents. Learning agents is an experimental plugin that allows you to do reinforcement learning and imitation learning in the Unreal Engine. Can't stress enough, it's experimental in the sense that it's still being developed. Daniel Holden and I co-created learning agents over the last 2 years or so, and we still have a lot more features that we want to add to it. So things will be changing. It's fully feature ready to ship in your game, but if your life's going to depend on it, things are going to be breaking. We still have a lot of things that we want to improve. So learning agents comes with an API for doing data collection, for training your agents using Python, and then for running your agents completely in Unreal with no Python at that point in time. So here's like a 10,000-foot view of the code structure. The primary class is this manager, which is an actor component you can just attach to any actor in your scene. And then you're going to add UObjects to that manager, which are going to be your agents. So in this example, we might have some cars that we were going to try to train. And then the manager sort of has that first responsibility of managing the agents. But secondarily, it's where you sort of compose your program. So you might be training, you might be doing inference, you might be doing imitation learning or reinforcement learning. All of that is defined inside of the manager. So you have a lot of flexibility there to solve the problem that you care about. And to help you do that, we give you all these manager objects, which help you structure your program. So with the interactor, that's where you're going to be wiring up the observations and actions. With the training environment, if you're doing reinforcement learning, that's where you'll define your reward function. And you can probably imagine what some of these other classes are for. So that was really quick. I want to dive in more detail on how do we actually get observations and actions. So this was a question that inspired us when we were working on the 5.4 version of learning agents, which is how can we make it easy for game devs to specify what an agent observes and what its actions are. So let's walk through an example. Let's say we're making a bot to play Fortnite, and we want it to be able to look at objects in its local vicinity and make intelligent human-like decisions. So all these objects might have different properties that we care about. With trees, for example, they're very simple. Maybe we only need to know their location. Chests are like an upgrade from that. We need to know if they're open or closed. Has someone else already taken all the loot? Guns, we need to know how much ammo is left in the clip. Should I reload now? Should I keep shooting? And then we need to know some really complicated things like other players. What's their speed, their velocity, whatever, rotation. So much information. So how can we make it easy for game devs to get all this data into the neural network? Similarly, on the action side, let's look at this simplified example. Let's say we want to move and shoot. If we're going to move, we need to pick a direction that we're going to move in, and we need to also pick the speed maybe. If we're going to shoot, we might have one hot encoding of all the different targets we're going to shoot at, and we need to output a 1 for the target we're going to shoot. So the way we solve this problem is by defining a sort of domain-specific language that it's going to let you define the structure of your data. And then we're going to take that structure and automatically generate a neural network for you. So this lets you think a lot less about the neural network and spend more time thinking about your data. And then learning agents, you're going to write a function not only for this schema language, but also for the actual data that's going to go into that schema. And then learning agents will validate all the data you feed in against your schema. So here's how that might look. With specify observations, this is where you're going to define the schema of your agent's observations. And it kind of looks like this. So you're going to read this from right to left. You're going to say, I have a set of objects. So those are all the objects around my agent. They have properties, for example, a location, maybe an enumeration of what type. Is it a tree? Is it a chest? Is it another player? And then you can have optional observations. So maybe I need to know the ammo count for the gun. And it works in Blueprints, but it also works in C# or C++. And I think the API here is a lot more elegant. This is great. This is great for everybody, but like that's just beautiful. So nice. Once we have our schema defined, we need to actually gather the data for the state of the game that our agent is in. And we don't have anything really new here. Basically, you can call all the functions you already know, like get actor location. You can use the existing AI perception system. So your schema sort of defines slots where you need to stick data in for the current state. And these slots are defined through these like make location, make enumeration, observation, et cetera. So those are going to sort of match up with what you had during specification. And then you can imagine that there's a very similar API on actions. So that was like a whirlwind of information. I have all of this built into a course on where you're going to train an agent to drive around the vehicle template that ships with Unreal. So you're going to learn a lot more about how do you specify these observations, actions, how do you do all this data stuff. And then we get into interesting things like how do I debug my machine learning? How do I save neural networks and load them? And how do I monitor my training with TensorBoard? So you're going to learn a whole lot more than what I was able to cover here. So, Fortnite. This summer, we published a paper called Human-like Behavior in a Third-Person Shooter with Imitation Learning. This was presented at the Conference on Games by our intern, Alex Farhang. So if we're trying to make a bot to play Fortnite, what are some things it should do? Here's two things, there's probably more. But the first is that it should prepare players for PvP. If the bots play in a human-like way, and players who are new are playing against them, when they transition to playing against real players, they'll have a better experience if those bots play like how players play. Right now, it's very jarring when you go from playing against the bots to your first match with real humans. They just play very different. So that would be a great problem to solve. Secondly, we want the bots to be able to adjust to their skill. We want them to be able to play in an intelligent way, but at a level appropriate for beginners. And then we also would like them to play really great for veteran players as well. You can imagine at the very top skill brackets, it takes a long time to do matchmaking. And if we can stick in bots to matchmake faster, but still have a great experience for those players, that's a great problem to solve as well. So how can we do that? Well, let's look at the current bot AI. So you can see Jonesy here is controlled by the existing AI behavior tree. He sort of picks a point where he's aiming and he starts shooting, and he kind of walks around in this repetitive way. And if you've ever played Fortnite Battle Royale, you'll know that you can pick out a bot from a real player very quickly. So they don't play in a very human-like way, and what can we do? Well, here's how we solve this problem, is we created a data gem, which is like a simplified level inside of the Fortnite client. You're gonna play in a repeated combat scenario where you're playing as Emmy here against Jonesy, who is the existing bot AI. He's gonna be trying to eliminate you, you're gonna try to eliminate him, and whoever, we're gonna be collecting data through that entire session. Whoever wins, we're gonna reset it and just keep playing through these repeated scenarios. So we wired this up with learning agents. We're gonna log out data of the current game state and then the actions that the player was taking. Once we have this little database of data, we can do offline training. We can create a model and then import that back into the gym in order to evaluate how our model works. So here's how you'd set up data collection with learning agents. You have your interactor, which is where you define those observations and actions. You have this controller, which is where you're gonna capture the actions from the input system. And then you're gonna use this recorder object in order to just grab all that data and output it to a file. And then Emmy over there is gonna add herself as an agent to the manager. So once we have this data, we have to pick a model to train. We decided to use this causal transformer, which is basically based on the decision transformer paper. And the way this works is we're gonna feed in a sequence of state action tuples. You can picture there's state 0, action 0, which is maybe the oldest observation and action that we have, and then we have a state T, action T, which is maybe the most recent state and action. And this trajectory is going to be 60 frames long, and if we're running the game at 30 FPS, then that means this is going to be about 2 seconds of information. So the model is going to take that in after tokenizing all these observations and actions, and then it's going to output the predicted action that should be taken on the next frame. So you can imagine that we can basically take the predicted action and compare it against the action that the player actually took and minimize the distance between those, and that's how we're going to train this. So once we've trained our model, we need to do inference. So we had our thing that we trained in Python. We're going to output it into the Onyx format. We can drop that Onyx model into the editor and run it using Nini, which is the neural network engine that ships with Unreal. We can wrap that up in a policy and then run that using the existing interactor that we created when doing the data collection. So here's the model that we were able to create. So Emmy here is controlled by our neural network. You can see that she aims and moves in a much more believable way. So our model is controlling not only the pitch and yaw of the controller, but it's also controlling the movement in terms of like your feet walking around, aiming down the sights, pulling the trigger, crouching, and jumping. So that was our first result, but just looking at videos isn't enough. You know, we're scientists, we want to have some hard data. So what we did was we took our model and we run it back in the data gym, and then we just log off the data, and we can use that to generate some stats. So here on the top, you can see some high-level combat stats. In the orange, we have the existing bot AI fighting against bot AI in our data gym. Then we have, in green, humans playing against the bot AI, and then in blue, the neural network playing against the bot AI. And you can see, as expected, like some sanity checks, like the bot playing against itself is going to have a 50% win rate. Humans are really strong, even stronger than our best bot, so they have a very high win rate. And then you can see that the neural network is much closer to the human behavior than the bots fighting against themselves. So, and you can see that trend exists across these different stats. So these like very high level stats do not tell you a story about, is this model human-like? So we need to look much closer. And we did this by looking at the energy of the trajectories. But the way to visualize that for the presentation is to think about the yaw here. So yaw is like the left-right rotation. And you can see on these two different graphs here, one is acquiring a target and the other is tracking. So acquiring is like this broad movement where there's someone over here I want to aim at. I need to do a big rotation, like 100 degrees. And then once my crosshair is pointed at them, they're going to be trying to move around. I just need to track them in order to keep shooting at them. So that's the difference between these two. So you can see here in the orange, the bots jump around. They just have these huge jumps. And the humans in the neural network, they move in a smooth way, and they'll overshoot and undershoot. And then you can see similarly here with tracking, the bot still is jumping around once it started tracking, versus our neural network and the humans move around in sort of a lot more random way. So that's really cool, but can we go further? Can we solve those problems that we talked about in the beginning? So here's how we could do that. We can split up our data into partitions. We can have, for example, different groups where we split it up by skill. We might have low skill data and high skill data. We can also split our data like this, just have individuals. We want to have our model play like any person in our data set. Then what we're going to do is we're going to train our model to learn a token, and then we can feed in this token at inference time in order to prompt our model. So this is very similar to like an LLM prompt, but it's a learned prompt instead of like a handwritten prompt. So we're going to feed that in every frame, and then the transformer's behavior will change based on what the ID that it's fed. So here we're going to compare like our high skill data group versus the low skill data group. You can see on the top that the bot is going to get killed much faster, and it's going to have a lot less offset. And down here, you can see that the crosshair is going to have a bigger offset. And eventually, it'll get a kill. But yeah, so you can see high and low skill. Here's some data. So we have high skill humans, which is the H high, and then high skill neural network in red. And you can see that the neural network and the humans match up fairly well. And compared to the blue, which is the lower skill group, you can see that the neural network has a much lower win rate in that. And then when we wanted to look at the individual IDs, it's kind of hard to tell, like, if I have two different people in the group, does the model play like the first person or the second person? So the way that we thought to figure that out was to just look at these high-level stats with crouching and jumping. So we might look at human 1 when the model's prompted with their token. The neural network will crouch a little bit because that person crouched a little bit. For human 2, they crouch a ton, so the neural network crouches quite a bit more. Interestingly, this isn't perfect. Like human 3 here crouched a medium amount, and the neural network wasn't really crouching at all. So that's something to figure out in the future. And you can see a similar pattern with jumping. And then I just want to remind you that all of this is running in the editor in real time. There's no Python at this point. You could ship this in your game if you wanted to. So here's some takeaways. We wanted to show that imitation learning can work and do something really useful, and can create a model that can actually run in real time and could ship in a real game. And then we wanted to show that this could work with a small data set. So we actually trained it only using data that we collected in our lab. It was about 8 hours of data. So this shows that this isn't a tool just for people with a Fortnite amount of data, but any startup or indie game developer could collect this data set if they wanted to, and could train a model to do something like this. And then we wanted to see that we could solve these problems of being able to prompt our model in order to have it display different skill and do other things, such as being able to imitate certain players in the data set. The thing that's great about this, and why I put the question marks, is because you can really train it to imitate any sort of behavior you want, as long as you can split up your data into those different buckets. So you can probably think of some cool thing you'd like to do. Maybe you want to have different personality for your agents. Like you might want to have an aggressive agent and have a passive agent or a hiding agent if it's like Battle Royale. So you can have more variety in your AI behavior, and that might make the game more interesting. So as long as you can split up that data, you could do that. So here's my call to action. If you thought any of this was interesting, you can find our paper online. You could also learn a lot more about learning agents by going to the course. So I want to thank you for your time, and I'm happy to take questions, and I'm always open to feedback.